Anyone there?
Yeah, Matt. I'm here anyway. I see some other people.
More than right now. It's pretty great.
Do you have access to share screen and everything?
Let me check here. I'm gonna try to sign in from my iPad as well, so I have the webcam going on.
Well, we'd all love to see your face, so that sounds like a good plan.
I don't want to deny anybody that gift. But will it allow me to sign in from two devices?
Spots at once? I don't know.
So we're going to find out right about now.
There it is.
Boom.
Very good. Very good. All right, we've got about 5 minutes before we're supposed to get started, so I think we'll just hang out until then. How do you want to do questions, Matt? Do you want us to interrupt you? Or you want us to save them till the end? Do you want people to be able to interrupt you on their own? What's your preference on that? I see your mouth moving. I don't hear you speaking.
Yeah. I feel like the theme for the past year could just be, sorry, I was on mute.
No worries. We're all used to it, I think, at this point.
You see my beautiful face now?
Yep, gorgeous. Nice ceiling fan.
I got my live studio audience behind me, the dogs.
All right. Looking forward to some heckling.
Yeah, I just hope they don't snore too loudly. They're pretty asleep, so.
Well, that's good.
Lighting in
the little
here.
One's quite.
What's
the little
that?
one's a diva, so we'll see.
Yeah, no kidding. Usually they're pretty chill throughout the day. I have a few moments, but. So yeah, I think for questions, Adam, do you want to try to monitor the chat and see if people can send in questions that way, or maybe sort of does this have the raise your hand option?
There is a raise hand option. Let's see.
Yeah, let's use that.
Do you see that? Do you see that I raised the hand?
I do see it. I don't know if I would see it if somebody else raised their hand.
Okay. Well, Dan and I will keep an eye out for that. So
yeah, if you want to, like, if we want to have most people on mute, just so there aren't too many issues with background noise, and you and Dan maybe stay, or keep an eye on the chat and the raise hand thing and try to get me to stop talking. If somebody has a question, then that'd be great.
Okay, we'll move forward with that.
Good.
Great. Let's see here. 20 people in here so far.
Yeah, we had about 50 in our final registration, so we'll wait a few more minutes before getting to go.
Last update, it was 55 here as of this morning.
Oh, great. I'm doing this in my basement here, but standing up so that I can still pace and fidget and stuff like I would in front of a real audience. I mean, a live audience.
We're real people, Matt, I promise. Even if you can't see most of us.
Yeah. Cards are man, there we go. Well, I'll just sit tight then, Adam, until you say the word.
Okay, that sounds good. For everyone who's already joined us, we'll plan to get started here in a couple more minutes. Let the rest of our participants get the chance to join.
Now we'll just pull up the ASHRAE Iowa website for you here to have something to look at. There you go. Close my.
Hey, Matt, go over to the resources page. And then scroll down to the bottom a little bit. I just put up the November chapter meeting recording up there for everybody on our YouTube channel. So we can put yours up after you're done today.
Cool. Is this thing all going to be recorded?
I believe so.
Cool. I'll try to watch my language.
Thanks for sharing those resources with us, Jason. That's great. That's great for everybody who missed our chilled water discussion. Did ethics pop up there as well? Doesn't look like it.
Everybody wants to go subscribe to that ASHRAE Iowa YouTube channel, they can.
We could do better than one subscriber, I'm guessing.
Yeah, that's me.
Two. There's two.
All right. Started the trend. All right, we've got a couple minutes after the hour. Let's get started. As people join in, they'll be able to catch up. This is Adam Pulse. I'm the chapter president for the Iowa chapter this year, and I want to thank you for joining us for today's virtual meeting. We have Matt Jessen from Systems Management Test and Balance to provide us an update on testing and balancing on the Airside, and hopefully can answer some questions that we engineers have from project to project. Matt's been in the HVAC industry for 20 years, and he's been focused on testing and balancing for the last 10. As we get into the presentation, we'd ask that you raise your hand or enter your questions into the chat. Myself and Dan Blake, our CTDC chair, will be tracking those and give you the chance to chime in with a question, either with your own voice if you'd like, or if they're in the chat, then we'll read it for you, and we can go from there. I don't think that there's any other real chapter news. We're really just happy that you're able to join us, and hopefully Matt can fill the rest of the hour, so I don't have to. Over to you, Matt.
Okay. All right. Well, thank you very much, Adam. Thanks everybody for tuning in. And if you, just in case you missed it, if you do have questions during the presentation, it's probably best if we leave ourselves muted. But if you have a question, use the raise hand feature, or type something into the chat, and then Dan or Adam will let me know to be quiet for a minute while the question gets asked. So I encourage questions, always welcome, and we'll have time at the end for them as well. So yeah, we'll be talking about air balancing today, and my goals for what I want to get across here. I'd like to help you gain an understanding of how tab instrumentation is used and its limitations. It's important to know how airflow measurement works in order to kind of understand some of the issues we're going to talk about. I'm going to talk about several specific challenges that we run into in balancing that can be kind of a roadblock to doing our job properly, and then talk about some potential ways of addressing those issues. So we'll get right into the first part here. Airflow measurement. How do we count up the cubic feet per minute that your system is delivering to a space? In principle, airflow measurement is very straightforward. If you have air moving through a duct, you just need to know the area and the velocity of the air. You multiply those two, and you've got your CFM. It's that easy. But as you can imagine, I couldn't really fill a full hour presentation just with that. So here's the things that can kind of complicate that. The first part of that equation that we're going to talk about, area. So if you're talking about a duct and you're measuring airflow inside a duct, that area is really straightforward and easy to define. But when you're talking about the measuring face velocity at a grill or a register, that area becomes a more complicated question, because you need to look at the area of the airstream, not just the area of the grill itself. So on the right, you can kind of see the diagram of the airflow coming through your vena contracta as it comes through the blades of the grill, and then it spreads out as it gets out of the grill. So that effective area is the area of the airstream that we're talking about that we need to know. And you can go and look up, for different grill manufacturers, you can look up some of these factors. So I have two examples here, both from the same grill manufacturer, two different models of grills. So 12 by 12 on the first example there has an AK factor of 0.89. So the effective area, the discharge of that grill, is 0.89 square feet. The other one, the one below, this one has adjustable blades. So it shows you 3 different AK factors for 3 different deflection degrees. So first, right off the bat there, you can see as you start deflecting these grills, it affects the effective area of the grill and therefore your airflow measurement. And it ranges from 0.55 down to 0.47. So for 2 different 12 by 12 grills, you can see you can go anywhere from 0.89 down to 0.47, depending on the model and how the vanes are deflected. So that can be a major difference in your airflow measurement. And I will point out that you can, you can find these factors on the grill manufacturers' websites in some cases. I have not always been able to find them. And if you're just going into a building and going up to an existing grill, are you going to know the manufacturer and model number of that grill? Most likely not. It's not exactly stamped on the front of it or anything. So there's always some guesswork to a degree involved in that, and some judgment required. The second part of the equation, velocity, is more complicated, really, because velocity profiles are not uniform. You have to find an average velocity for the airstream, which requires multiple points of measurement across its area. So if you're doing a duct traverse, you need to have some straight duct length. You can see on the diagram with the fan, as the air comes out of that fan, all the velocity is pushed up toward the top of the duct, which makes sense. That's the direction the fan is rotating. And it's just pushing all the air up there. Down toward the bottom of the duct, the air becomes stagnant or even moving backward. There's an eddy there. So if you were to try to take a duct traverse right here, it's going to be all over the map and very inaccurate. Your airflow is turbulent. As it gets further down, it starts to even out. But even once it's fully developed flow, it's not just straight down. It's not all equal velocity all across the area, because the sides of that airstream kind of stick to the duct, and it creates that kind of D shape. So you need to take an average velocity, taking all of that into account. The other diagram there with a parallel blade damper that's about halfway open is very similar to the fan. It pushes all the velocity up to the top of the duct, and you get turbulence downstream. So let's talk about how these are measured and what we use in the field. A duct traverse is hands down the best way to measure airflow. It is the most accurate. And what you can see on the picture there, how a duct traverse works is you drill holes in the duct, you insert a pitot tube, and you take multiple velocity readings with the pitot tube for each hole. Essentially what you're doing is creating a grid of velocity measurements. That is my dog shaking his collar. Sorry about the noise. So you give this grid that you're making of velocities across the area of the duct, and you average them out. The pitot tube is the classical tool for this. It was invented in the 18th century, and it has been changed very little over the decades and centuries. It's a very accurate instrument. It operates on extremely straightforward principles of physics, and it can be used with just a simple manometer. There are other instruments that you can use for duct traverses. The airfoil is one, and it's a lot like a pitot tube, but with a straight end instead of the 90 degree. And it works very well and very similar, but it requires an algorithm that's developed by, and it's sort of proprietary by the manufacturers of these instruments. You can't just use a simple oil-filled manometer to determine your differential pressure. And the hot wire anemometer is another instrument that some use, operating on a thermal dispersion principle. The only issue that I'd bring up with the hot wire is that most hot wire anemometers do not know what direction the air is flowing. It just knows the velocity. It could be going the wrong way, and you might not be able to tell just by a velocity reading. Again, depending on the particular model. The only real drawback to a pitot tube duct traverse is you have to find a location for one. You have to have enough straight length, and you have to be able to access it. So what does that mean? What do you really need for a good duct traverse? So this is a diagram of an ideal duct traverse location. You need downstream from an elbow or a change in size, a takeoff, anything that interrupts flow or changes it. You need 8 duct diameters downstream, and then another 2 duct diameters upstream of another interruption. And so if you're talking rectangular duct, then you need to do a little math to convert to an equivalent diameter. But to make the math simple, for a traverse in a 24 by 12 duct, you need 153 inches downstream of an elbow and 38 inches upstream of one. That's about 16 feet total. That's quite a bit of distance that is sometimes not feasible for a particular duct. And bear in mind, this is for a 24 by 12 duct. That increases as you get bigger duct. It isn't always 16 feet. Now, if you can't get an ideal duct traverse, the next best thing is a non-ideal duct traverse. If you have some straight duct, you can always try to get a duct traverse in it, and you can evaluate the velocities that you read, the velocity pressures in the grid, and see if it is basically, if they are even enough to use as a proper measurement. Other tools that are used in TAB for face velocity measurement, the rotating vane anemometer, the one that you see on the left picture there, is a digital model. There are also just analog models that have been around for decades that work perfectly well. That's the kind that I've used mostly. But you put that right up against the grill and read velocity that way. The VelGrid to the right there is a plastic grid with basically, pairs of holes to measure pressure across the face of it, and that is sort of a proprietary name there, VelGrid, but there isn't really another alternative. You can also use airfoils and hot wires to read face velocity measurement, but the rotating vane and the VelGrid are the most common. The drawbacks to these tools are this is where your effective area that we were talking about really comes into play. So you can see on these diagrams, the rotating vane is put up right against the surface of the grill, and you move it across the grill over time, to get an average of feet per minute across the face of a grill or register. So if you have that AK factor, you can pretty much rely on that. The VelGrid, however, if you put it right up against a surface of any kind, it kind of blocks those holes. You might be actually skewing it by doing that. So it comes with these 1.5 inch legs or standoffs that hold it off of the surface 1.5 inches. So on this supply grill, you can see the plane that you're taking that reading in is after the air comes out of the grill and starts to spread out a little bit. That becomes really difficult to evaluate. What is your effective area? What's the area of that airstream then? And it'll change depending on the type of outlet. Another thing to bear in mind is that the VelGrid averages velocity pressure, not velocity. And I didn't want to put a whole slide in here with the mathematical proof of this, but hopefully you engineers will recall that velocity is a function of the square root of velocity pressure. So if you take the sum of a bunch of square roots versus the square root of a sum, you get very different results. And taking the average of those velocity pressures and then calculating it is simply a less accurate way of getting your average velocity. So math aside, the point is that the VelGrid will be a little less accurate than other methods, and that will vary depending on the velocity profile. If the velocity profile has a lot of variation in it, then it gets worse, basically. If you really want to go through the math sometime, I'd be glad to go through it with you. And then finally, what the tool that most people associate with balancers is the flow capture hood. And it's available. There's several different manufacturers, and you can get different sizes, different hood tops. So the blue one that you see there is set up for 2x2, and that's really the hood's bread and butter, 2x2 ceiling diffusers. It reads those really, really well. The red one is set up for a linear diffuser. It's just a different top on a similar base. And the clear hoods that you see in the top right, that's actually like a lower flow hood that's better at capturing low CFM values. And it has two different tops there that's showing. Drawbacks to the hood, first of all, it's just too dang easy. And I'm only partially joking about that. It is so easy to use that it can give you kind of a false sense of security. We'll talk in much more detail about that later. It doesn't read accurately in some applications. You might need to take a duct traverse for comparison. And finally, it creates back pressure. If you kind of take a look at the bottom right here, what the hood does is the airflow comes out of your grill, it spreads out, it hits the sides of the hood, the fabric, and it kind of washes against that. And the hood directs it down through the measurement device. And the measurement device in the flow hood is typically, going backward here, is typically something a lot like this Velgrid. That's what's in the base of the hood. It directs the airflow across that and is attached to a meter that's located on the hood base that goes through an algorithm essentially to calculate the flow. So part of what it does is it actually creates back pressure. You put that up against a diffuser and it'll actually decrease the airflow coming out of it to some degree. So that can skew how it reads. And most of the models that are out there have some sort of method for what's called back pressure compensation to try to calculate like what would the flow be if I didn't have the hood up against it. So that can be an automatic function of the meter, or it can be a manual function. So to get into the actual specific challenges I want to talk about, the first one is one that I wanted to make sure that we covered because it comes up very frequently. Pretty much any job that has rooftop units, this will come up. And it's outdoor air for rooftop units. Rooftop units will usually have a minimum requirement for outdoor air because code, but it is really not possible to measure that outdoor airflow directly. If you take a look at this picture, you see the hood where the outdoor air comes in. What is my effective area going to be there? We talked about how that the area of your airstream isn't the same as just the area of the opening. Could I take a Velgrid or something and put it up against this and get a reading? I certainly could, but I don't know what to do with that reading. I don't know what to multiply it by. I could take a guess, but that could be all over the place. Also, your airflow right here is going to be quite turbulent. If you think about it, most of the time, the outdoor air control damper is going to be right behind this. And when you're at minimum outdoor air, it's going to be throttled back quite a ways. And so that's going to create more turbulence. And finally, you're outside. Wind is a factor. Any little bit of wind can really skew a reading that you're trying to take. So measuring that directly just isn't an option. But what are our options? So the first one is arithmetic. You could take your outdoor air should be the difference between your supply air and return air, right? That's pretty straightforward and true. What you need in order to use that method are, first of all, accurate readings on your supply and return air, by which I mean good duct traverses. And this is usually what will become an issue when you're trying to do this, is that return air. You know how on a rooftop unit, most of the time, if you've got a wild return, you've just got at most maybe a drop coming through the roof and an elbow for sound. That's not enough to get a good duct traverse. We're not going to be able to get an accurate reading on the return air then which kind of throws this method out the window. You need good tight ductwork, minimal leakage, which is always a good thing. But if you have too much leakage between your traverse and the unit, that can throw this off a lot. And you need to have no airflow going through anything else. Nothing through the relief damper or exhaust fan. You think about it, you just draw your box, and your box has return air coming in, supply air going out, outdoor air coming in. If there's anything else, then suddenly that arithmetic doesn't work. One thing to watch out for, even if you do have good duct traverses and all the conditions are right for using this method, one problem that you might run into is if you have a really low percentage of outdoor air, it could actually fall within the tolerance of the measurements. So even a good duct traverse has some uncertainty. The accuracy is limited on tab instrumentation. So let's say you got a supply reading of 8,000 CFM, that could be plus or minus 400. A return, 7,200, could be plus or minus 360. So when you do the math and come up with your outdoor air, that's 800 CFM of outdoor air plus or minus 760, which basically might tell you you might be double what you think you are, or you might be almost nothing. Now, I'm sure that somebody who's better at statistics and such could really tear into me for how I'm adding together the uncertainties, but I think the general idea is valid. That I call this trying to control small numbers with big numbers. It's difficult to do, and it can throw you off a lot. So what other options do we have if you can't do the arithmetic version? One is to try it by building pressure. Blow up the building like a balloon, by which I mean you just adjust that outdoor air damper until you get the building to be a slightly positive pressure, if that's the typical goal. What you need for that to work, first of all, you need to have a pretty small building that's tightly built. Obviously, trying to pressurize a space with 1 RTU, and if it's a big box store or something, that's not going to be feasible. So you want it to be pretty small, and preferably just 1 RTU system, so you don't have anything interacting with it. Other things to watch out for: if it's a windy day, those building pressure measurements can be skewed quite a bit. And also, if your building is pretty leaky, this could end up giving you too much outdoor air, and then of course giving you capacity problems on your rooftop unit. So hopefully with an experienced tab technician, that would be fairly obvious if they're trying to do this. If you're trying to pressurize a small building with your rooftop unit outdoor air, and you're opening it up, and you're like, okay, hey, there we go. I finally have a slightly positive building, and my outdoor air damper is wide open for minimum outdoor air. That should be a red flag. So that's where kind of the next method comes into place, and that's, you can make an educated guess, estimate what that minimum outdoor air damper position should be. Usually a minimum outdoor air on a rooftop is going to be somewhere between 0 and 20%. And I say 0 because most of those dampers, even if they're fully closed, will get some airflow through them. There's some leakage, and in some cases, that could be 5% of your supply air. So if you have experience in tab, you might have some rules of thumb developed that say 0% gets you 5%, 5% gets you 10%, by which I mean a 5% damper position gets you 10% of your supply air through the minimum outdoor air. And it's important, if you do this, to record what that setting is and how you determined it, and include that on the tab report. And I should point out that sometimes that outdoor air damper position is set through a controller or through the DDC system, where you actually dial in the exact percentage and it goes to that position. But on some rooftop units with simpler controls, it might just be a little potentiometer on the control board of the rooftop unit, in which case it might not have a percentage that you can really mark down. So what we'll do sometimes is go to the damper itself once we've got it set where we want, and just measure the gap in between the blades and say the minimum outdoor air damper position was set to 3/4 inch of open, which provides a good way to check it in the future. Once again, you just got to be careful that you don't bring in too much outdoor air and give yourself temperature problems. Probably best to err on the low side with this method. So you might be thinking, okay, what about this? What about that? A couple other things that usually come up. One is the temperature method. You can calculate your percentage of outdoor air based on comparison of the outdoor air, return air, and mixed air temperatures. And that's totally valid. And I have done that a number of times. What you need, though, is first of all, you need a good, accurate average measurement of your mixed air temp. If you take a single point temperature of mixed air, that probably will not give you a very accurate result. If you've got a good averaging sensor in there for like a DVC system, then that might work much better. The other thing you need is a big temperature difference. You can't do this when it's 75-degree return air and 70-degree outdoor air. It just won't. It's just too tight of a delta T. So it's best if you've got 30 to 40 degrees of difference between outdoor air and return. So if you can control the weather, that's ideal. And what about factory airflow stations? Factory installed outdoor air monitoring stations on the rooftop units. That's one that we get asked about a lot, and so I've kind of brought it into the whole next challenge section here to talk about in more detail. Airflow stations. I should say that airflow stations themselves are not the problem. They are great. They're great tools for getting your system under control and doing monitoring, but you just have to keep in mind the limitations as usual. They have to be installed correctly in a suitable location. The tab agency needs to be able to verify and calibrate them, and they need to be kept clean. It's all about location, of course. If you think of an airflow monitoring station as being similar to a duct traverse, and going back to the straight duct required for a duct traverse and how it works, getting the multiple points of velocity, most airflow stations operate on exactly the same principle. So the manufacturers have their recommendations out there for where to locate them, and go by those, but bear in mind that if you've got good straight ductwork, that's your best case scenario. And if a test and balance technician can't measure that airflow, then can you trust what the airflow station is reading? Again, nothing against airflow stations, but there's many things that can affect their reading that might lead you to get an incorrect airflow measurement. So let's take a look at this particular installation. I'm going to say out-of-state engineer, out-of-state contractor. But these are on the outdoor air intake of a rooftop. And we talked about area and velocity. First of all, what's the area in that cross section where that airflow station is located? It's a sloping duct, right, coming right off the intake. And I would imagine that airflow is going to be very turbulent there. Are those two velocity readings in that station on each one positioned just right to get the average velocity? It's a little hard for me to believe that they are. Also, you might note that those look pretty exposed to the weather. And in fact, in this particular case, they got flooded and failed. So you got to be careful as to where you put them. Also, they have to be kept clean. Most of these airflow stations, this particular type that's shown, operate similar to a hot wire anemometer. They operate on thermal dispersion. As the airflow goes through, it cools an element, and that provides you your velocity. If they get dirty, that kind of acts as an insulation around that element, and it'll read falsely low. And this is something that we have encountered many times. If these airflow stations are being used in a building pressure control sequence, if you're determining how much air to exhaust based on how much outdoor air you have, this can throw your building out of whack in a hurry. And if we get calls for buildings that are having building pressure issues, this is one of the first things I'll look for. And in this particular picture, I got on top, there's this huge air handling unit. So I had to get up on top of it, 10, 12 feet in the air or whatever, crawl inside a duct and crawl down, 15 to 20 feet to get to this airflow station. And I wasn't at all surprised when I saw that it was this dirty. But often with these, you can clean them with compressed air or a little paintbrush. You don't want to, spray Windex on them or something. But once you clean them off, often it'll just come right back to where it used to read, and building will come under control. So first of all, if you can put it in a filtered airstream, please do. Second of all, make sure there's access to it and that the maintenance staff knows that this is something that they should check on a regular basis. Sometimes I know that it's not feasible to get it in a filtered airstream. All right. So,
hey Matt, we do have a question about airflow measuring stations.
Excellent. All right, what do we have?
Okay. If we have an airflow measuring station to measure minimum outdoor air in a rooftop, such as the Ebtron that we were looking at or something similar, assuming it's engineered to be located in a dedicated minimum outdoor air laminar flow area, why does the tab apply a correction or adjustment to the airflow measuring station readings, considering the difficulties of measuring outdoor airflow for an RTU?
Okay, gotcha. I think I understand what's being asked, and I believe that might be answered in the next slide here, hopefully. So when we talk about calibrating airflow stations, that might be kind of a bad word to use with the airflow station manufacturers. They are factory calibrated typically. And what their literature will say is that they need to be confirmed, validated, et cetera, by the tab technician in the field. So when we tend to refer to it as calibrating, because typically we will take a measurement, compare it to the airflow station reading, and adjust a gain factor or some sort of correction factor to obtain a similar reading on the airflow station. If it's very close, we just leave it as is. So in this instance that we're talking about with an airflow station that's located in a minimum outdoor air laminar flow situation, I think that, if it's a dedicated minimum outdoor air opening, you've got a much better chance of it being accurate right out of the box. And I'll show you right now kind of what we'll go through on like a rooftop units situation in order to try to confirm these or calibrate these airflow stations without getting a direct measurement. The first is that you've got very similar options to what we just talked about with measuring rooftop unit outdoor air. If we can get a good supply minus return with good traverses, then I would hang my hat on that as compared to the airflow station reading. And I would also gut check, based on building pressure, outdoor air damper position, or actually we just did this with an outdoor air temperature comparison. And if everything seems to make sense, if the outdoor air damper is 0 to 20% open, building pressure seems in line, mixed air temperature seems to make sense. If you've got a factory installed airflow station, I would leave it reading as is. I think the only reason I would change this is if I had good solid numbers to back that up with, which would be supply and return traverses. Hopefully that answers the question. If not, please ring in again. Another option would be to measure the supply airflow with the unit running in 100% outdoor air mode. It can be a little bit tricky, and what you might have to think about is, do I want to calibrate or confirm this airflow station in minimum or maximum outdoor air mode? So airflow stations will typically read very well at whatever airflow they're calibrated at. And some have a 2-point calibration sequence that you can use. But once for most of them, if you get to double the flow that it was calibrated at, or half the flow it was calibrated at, it might read off by quite a bit. So the question might be, what's more important, the reading when it's in minimum outdoor air or when it's at higher airflows? I would say my expectation would be that it's usually more important to get that minimum correct, because that's when the CFM is important. And when it goes into economizer mode, it's really about maintaining the temperature, mixed air temperature. The exception to that might be is if it's being used in a building pressure control sequence of some kind, that might be important that you have an accurate reading at the high end. So if you're going to calibrate it in minimum outdoor air mode, the one limitation might be is if you can dial back the supply enough to match that minimum. Because again, what we're talking about is closing off the return air, it's putting all our airflow through the outdoor air damper, and then your supply air reading should match your outdoor air damper, provided that there's no leakage or other air getting introduced somehow. So in some cases, if your minimum is pretty low, it might be difficult to dial back the supply or to get an accurate reading at a really low speed. And it's also important to note that your damper position might affect how your airflow station reads. Often these airflow stations end up getting installed right inches from the outdoor air damper. And if that damper is just cracked open, that could read very differently from the way it will read when it's fully open. I've actually also seen in an air handling unit having an exhaust air damper or relief, and the airflow station was installed on the inside the unit just under the exhaust damper. And when that damper was fully closed, it would still read airflow because there was just this turbulence around that airflow station inside the unit. So I think it ended up having to be relocated onto the other side of the damper. That is it for airflow stations right now. So if there were any more questions on those, please send them in to Adam or raise your hand. But for now, we'll move on to lies my instruments told me. You need to use judgment when you're using instruments to make sure that you're getting accurate information. The hood is the balancer's best friend, really. I would not want to do a job without one. They are great tools, but they kind of function sometimes as the make it easy button, and you have to use it right, obviously. So in this case, can you put a hood up to a grill like this and get a reading? You sure can, but is it going to be correct? If you can see in this that through this clear hood, the top and bottom of the hood are not sealed off to the duct or anything else. So it's just open to the air there. Air can flow in and out of there as it pleases. So don't be like this guy, which if you don't know, that's me demonstrating how not to use a hood. My defense is I got a number. Yeah, you can certainly get a number, that's for sure. But is it reading CFM? It says so. Like I said before, the hood has a meter that's usually mounted to the base of it, and you hold it up to a diffuser, you hit the button, it clicks a few times usually, and then it'll tell you 153 CFM. So it's important to understand how it's getting there. As we were kind of talking about earlier with this diagram, air comes through the diffuser, spreads out, hits the sides of the hood, washes against those sides, and comes down through what is like a bell grid usually. But what that's doing is averaging multiple velocity pressures back to our square root of the sum rather than sum of the square roots. It's a little less accurate depending on how even this velocity profile is. So it's really important to know that the hood might not read accurately, especially on outlets that have high throw that create jets of air, like those eyeball type nozzle diffusers, security grills, drum louvers. If you think about how the air is moving through that hood, in the case of this, what I call eyeball, I'm sure there's a better word for it, but everybody knows what I'm talking about when I say eyeball, I think. It's directing that air in a narrow jet, and usually you see them in airports and big open offices and stuff to throw that air as far as it can. Well, when you do that, it just kind of hits one area, a tight area of the velocity grid in the hood. So that's going to give you a weird reading. And back to the square root of the sum rather than the sum of the square roots. That's really where that comes into giving you a bad reading. On linear slot diffusers, it can read pretty differently than it does on a square ceiling diffuser that's spreading the airflow out. If it's coming straight down or kind of directing it to the side, it can create like a sheet of air that sticks to the hood side, and it can read that really differently. Or it can blast right down through, similar to the outlets we were just talking about. So I've also experimented with on slot diffusers, if you're using like the square hood on a 2-foot wide slot diffuser, if you put it smack dab in the middle versus on the edge of the hood, you can get two very different readings. Okay, so what can we do about it? Sometimes your hood is going to lie to you. So what do you do about it? The first one is, the same old song, get a duct traverse. In fact, the hood owner's manual actually tells you to do this. It says to confirm your airflow accuracy by performing a pitot tube traverse and comparing that with the results obtained with the flow hood. So it's important to determine, is your data repeatable? Can you get a consistent result? So on some outlet types, you might not be able to read that same number twice. And a great example of that is going to be those eyeball diffusers. I've tested this out where I would take the hood and put it up to that eyeball diffuser, hit the button, take the hood down just to look at the meter to see what that number is, take the hood and put it back up and try to get it positioned just the same way, hit the button again and get a very different number. So on when that's the case, you just can't use the hood. And I can tell you that using the hood on eyeball diffusers and on most drum louvers and stuff is just not going to get you a consistent result, and you need to find a different way to do it. So finding an alternative, the rotating vane, the bell grid, something like that. A duct traverse is always good if you can get individual traverses on the outlets. In the case of the eyeball diffusers and this test that I did, I ended up finding that the rotating vane actually read very accurately on them. And you just put it right there in that opening. Those particular eyeball diffusers were sized just right for that too, I should say. The rotating vane fit right in it. If you do get a consistent result, even if it isn't an accurate result, like if you are reading an outlet and the hood tells you it's 150, but your duct traverse tells you it's 125, then you can just develop a correction factor, a K factor. And this is what the manual tells you to do. And the hood is meant to be a proportioning device, not so much an airflow measurement device, but a tool for proportioning the outlets. So the hood, and I should point out that this is nothing that the hood manufacturers don't know and that they aren't upfront about. This information is really all in the manual. It tells you, that the hood might not be consistent on some types of outlets, that you should do a traverse, all of that. So on to one of my other favorite subjects, face dampers and why I don't like them. I wanted this to be more than a list of things I don't like, but this is one that I think you'll hear from a balancer at some point, if not repeatedly, and for some people it's a bit of a surprise. When I talk about face dampers, I'm talking about these dampers that are typically mounted to the back of a grill and that are adjusted through the face, usually just a little screwdriver type adjustment. The problem is that they're bad for balancing. They change the effective area of the outlet. So if you can imagine back to that diagram with the vena contracta going through the grill, the blades of the grill. Well, when you start closing those dampers down, that changes that airflow pattern, and it affects how your reading is going to come out on the other side. So that can make it a moving target that's really difficult to judge. They make noise, they rattle, they create air noise because they're right there at the outlet. They collect dirt and debris, they rust shut. They can be adjusted later by the occupants, which if you're the occupant, maybe you think that's a benefit, but it kind of begs the question, why are we balancing it in the first place sometimes? And they're just plain less effective in diverting airflow than a decent damper in the duct would be. But sometimes you're stuck with them. So what can we do about it? Well, I'll go back to avoid them if you can, honestly. Best to just have good dampers in the ductwork. But if you can't avoid them, and I realize that's the case because sometimes access just forces your hand. One of the best things you can do is install branch dampers. So I kind of traced this example out of a prison job. In prisons, of course, access is always going to be a real challenge, and putting accessible dampers in all over the place is not realistic at all. So in this case, we have a branch that goes out to 4 cells, and each one of those has a supply grill with a face damper. Not a lot you can do to get better dampers out here. But if this is out in a secure corridor or something where you might be able to get access to it, plus it would be 1 access point instead of 4, then a branch damper here can help a ton, because you can cut this to get your total airflow for these 4 grills, and then you don't have to close down those face dampers so much, because that's when they really become a problem, is when you have to close them off all the way or nearly. It gets to be really difficult to do. And finally, you can kind of just embrace the fact that they're not going to be perfect. Maybe it's something that you can just live with in this particular situation. If you've got an open area where all the airflow is getting to the room, but with face dampers, it's just very difficult and sometimes not possible to get those outlet airflows to design. There are going to be some that are fully closed and still over design, and some that are fully open and still under. And that might just be how things turn out if you have to rely on face dampers. Just trying to be realistic with that. And we get that question a lot. In one case, working on a large project with a lot of these on a constant volume system, and they wanted to change to face dampers, and because they had remotely accessed duct dampers specified. And I gave them my honest opinion, just as I have here. And to my shock, they listened to me and they did not put in face dampers. And the sheet metal contractor is probably still angry at me about that. Sorry, guys. But we were able to balance it in the end. So speaking of tolerance, let's get into specified tolerances here. What I'm talking about are in the specifications for each job, they the engineer will provide tolerances for the airflow in the balancing spec. And the classic example is plus or minus 10%. And it's important to have meaningful criteria. You have to have something to judge this by, some sort of target to hit. But what I want to examine is, can the specified tolerances be achieved with the particular system that you have? And if not, then how's that going to affect operation? Is it a problem? So important thing to note here is that tab readings are just not perfect. Even when used properly, your flow hood accuracy is plus or minus 3% of the meter reading and plus or minus 7 CFM. And this is right out of one of the manufacturer's manuals. That is for a range from 100 to 2500 CFM. So if we do the numbers on that, at a hood reading of 100 CFM, the range of that is really plus or minus 10%, just as far as the hood accuracy is concerned. And as you go up in airflow, that range gets a little tighter. By the time you get to 400 CFM, it's under 5%. But still, you know, most scientific measurements are tighter than your airflows. So if the specifications call for plus or minus 5% at the outlets, is it realistic? So I'm going to go into a few examples that are directly out of specifications that I've worked on. And here's one that is really popular with a certain federal government agency. It says air outlets and inlets shall meet the following airflow tolerances: -5 to plus 10% for airflow rates above 100 CFM, -5 to plus 5% for airflow rates 100 CFM and less. Now, going back real quick to our chart here, I should point out that the published accuracy of this flow hood doesn't state anything below 100 CFM. And if you kind of look at the trend of these numbers, it's not getting better as it gets lower. So you can probably guess that when you're below 100 CFM, at best, you're plus or minus 10% just for the accuracy of the hood. So with this particular specification, what are we expecting? So your test and balance agency may be able to obtain measurements that are inside these tolerances, but first of all, it's going to be more time consuming and expensive. You might be surprised at how long it can take you to chase around 5 CFM. So is there value to that? Maybe there is in this particular project, but it's a question of I think something that the engineer needs to consider and maybe discuss with the TAB agency. Other thing to keep in mind is that the measurements may not prove up based on these accuracies. If you have an outlet that requires 50 CFM and the balancer gets it down to 50 CFM, you might come out with a different balancer with a different hood, both of them perfectly qualified, both hoods working perfectly fine, and you might get a reading of 55 CFM or even further away. So it might not prove up to be within that tolerance that's specified. My big problem with this specification really is as our ability to measure the airflow gets less accurate, the tolerance gets more stringent. That this whole -5 to plus 5% when you get down below 100 CFM, it's kind of going the wrong way as far as the ability to measure it properly goes. Another spec example that we run into, this is for rooms that require pressure relationships. So labs, hospitals, etc. So in this case, it says that airflow rates are, for spaces where airflow rates are used to maintain pressure relationships, tolerance for supply air outlets shall be 0 to plus 10% of design flow rate. So if your outlet is shown with a design flow rate of 260, you may not be below that. You have to be 260 to 286, right? if I did that math right. So issue with this, as far as the accuracy of the instrument goes, it's not too bad. But what kind of system do you have and how does it operate? In this case, you've got a VAV system. And this VAV serves this room for a total of 525 CFM. So let's talk about how we balance this. The VAV system balancing procedure is, first of all, you measure the total airflow for this box, and then you calibrate the flow station in the box. So once that's done, the controls will maintain that airflow rate of 525 CFM. But of course, it's not perfect. It's going to vary a bit, maybe 510 to 540. It might be even tighter than that, but let's just say it's 510 to 540. That's going to be your total airflow in reality coming out of that box. So our next step is to proportionally balance the outlets. I want 260 on this one, 265 on this one. So I'm going to measure them with the flow hood and adjust one of the dampers to get them proportionally in balance. But if the box is below, if it's a little below that 525, or realistically even exactly at 525, how can I get both outlets to be at least their design airflow up to 10% above? In this case, you know, the issue really is that the way that the system controls and the control tolerance is sort of in conflict with what my specified tolerances are for balancing. So what can we do about that? And this is a question for the engineer really. Is 525 the absolute minimum airflow that you need in the room? Can you not live with 510 CFM? Well, if it absolutely has to be 525 or higher, then it's pretty simple to just increase the total CFM set point for the VAV. And then you can make sure that it always stays above that 525. And if not, I would say just adjust these tolerances to plus or minus 10%. And I didn't put this in here, but another thing that we see sometimes is a tighter tolerance on the terminal unit, on the VAV, than on the outlets. And I'm all for that. I think that's a great idea, because you can really, most of the time, you can really dial in that VAV airflow much better than you can the outlets. Another example, and this is really just a continuation of the previous one, is, again, we're talking about rooms that require pressure relationships. It might say that your supply air is 0 to plus 10% and your exhaust air is 0 to minus 10%. So you can err on the high side on supply, but err on the low side for exhaust. Well, what we have to consider on this one is, how does this system operate where you've got room pressure control? Is the exhaust modulated to maintain room pressure, or is it balanced to a constant airflow? And if it's minus 10% of design and the room pressure isn't being met, what do you do? So typically that requirement is really driven on how tight the room is built, something that we all have very little control over. So this is one that typically as the balancer, I would discuss with the engineer to determine, okay, we're trying to get these, if the goal is to get this room to a pressure of positive 0.02 inches, how far down can I go with the exhaust? Can I go to half of its design flow rate if needed, lower, or is there an absolute minimum exhaust that we need to maintain? And if it gets down to that point, do they need to look at taking further measures to tighten up the room to meet that room pressure? So really that's the end of the specific issues I want to talk about. In conclusion, I want to say that so many of the problems that we have and that we run into during tab just come down to not being able to take a good duct traverse. If you can get good straight duct lengths in there, that helps you and it helps us. It helps you because it reduces system effect as well. It improves the performance of your buildings. If you don't have room for a good duct traverse, then you're also not getting fully developed flow, and you're increasing your pressure drop in the system. We are, of course, brilliant geniuses, but we're not magicians, unfortunately. During design and construction, think about balancing. Think how it's going to be pursued and implemented. And because it has a really direct impact on how your system operates. If a system can't be balanced properly, it's probably not going to operate very well. And you'll have comfort issues, noise issues, performance issues. So, and I think that all TAB agencies out there would agree with me that we encourage engineers to call us when they're in the process of design, or contractors to call us while they're installing or detailing their job with questions. You know, hey, will this affect how you balance it? Is this going to be do you see this being a problem, etc. We love to give feedback on that when asked, and you're more than welcome to call me or any other TAB agency to ask those questions. So that's really all I have, and I want to thank you guys very much for listening. I hope this has been helpful. I hope that it hasn't been too brutal, and I'm glad to take any questions that you've got.
Thanks, Matt. Really appreciate your presentation today. I know I've learned a few things and do every time we talk about the subject, so it's very useful for me personally. We did have some other questions come in. They said end of presentation, so I didn't want to interrupt, but
Okay.
The first one was, is there a minimum number of traverse measurement points when using a duct traverse?
Yeah, that's a great question, and there are TAB manuals that essentially, and standards, like my company is in AABC, the Associated Air Balance Council, and their standards would provide what those what the minimum requirement is for different sizes of duct. So it all depends on the size of duct. General rule of thumb for most reasonable duct sizes, you want to go somewhere in between 4 and 6 inch spacing when setting up a duct traverse. And in round ducts, there's a requirement that I believe is, I believe it's 16 read. Now I'm gonna lie to you somehow. But round duct traverses are a little different because you have to space your readings differently, because you're basically forming like concentric rings of equal area. So if anybody has a particular question on that, feel free to reach out to me and I can get you the exact data out of our manuals. Got no problem doing that. Quoting it off the top of my head is going to get me in trouble, I think.
Second part, kind of similar to the same point, I suppose. Can you define use of an equal area versus a log T duct traverse difference?
Yeah. Okay. So an equal area traverse is simply you are spacing the holes that you drill and the measurements that you take at even intervals. So what you end up doing is each point that you take a velocity reading at represents an equal area grid inside the duct. There's another method that's called log T. The T stands for a name that I don't think I can pronounce properly, Techeboff or something like that, which was developed through research to represent a proper average velocity in a duct based on not equal area, but kind of a weighted average. And I don't know that I can explain it in a really concise way. I personally, I'm more of a fan of the equal area method. I think it's tried and true, and it leaves less room for error, because what you have to do with the log T method is instead of measuring, okay, this is my 12-inch duct, and I'm going to drill a hole at 2 inches, 6 inches, and 10 inches. So even spacing of 4 inches, and then take my readings similar. You have to take that and multiply it by factors and determine, okay, my first hole is at 1 3/8 of an inch, and the next one's at 3 15/16 of an inch, or whatever. To me, my personal resistance to that method is simply that I think it leaves more room to make a mistake with arithmetic in the field. I'm not going to say that it's less accurate. Some research has indicated that it's slightly more accurate than the equal area method. So again, if someone's curious about the log T method in particular, I can get you the formulas for how you calculate the spacing and everything.
Thanks, Matt. I haven't seen any further questions come in through the chat, so if other people have questions, now's your chance. Raise your hand or add them to the chat. In the meantime, thank you again, Matt, and thank you everybody for joining us. We will cover some more balancing later this year in our March meeting, so if you're interested in the hydronic side of balancing as well, tune in for that. Haven't seen any more questions come in, and we're after 1, so I think we're going to call it. Thanks again, everyone, for joining us, and hopefully we'll see you at a future meeting.
Thanks, everybody. Take care.